Hi everyone and welcome back to your channel Structural Analysis for FE and PE exam. So we have a cantilever beam with a triangular loading which start at 0 at this fixed support at A and increase gradually to reach to the maximum intensity of W at the free end B. We want to calculate the maximum deflection of beam at free end. Let's start our problem. So in this problem, first of all, we can have our resultant force. So this is a triangular loading, so the resultant force is definitely half of WL, which is located at 1/3 from the base, which is the overall intensity. Mhm. And definitely the overall load, which is the resultant force, should cancel out by the only reaction at A, which is a half of WL, and moment at A is just arm, which is 2/3 of L, the other length times the force. So that's 2/3 of L times a half of WL, and it simply cancel out 2 and it just says WL squared over 3. So that's our MA. So as soon as we have our reaction and we have like our moment at the fixed support, we can cut our beam through by a length of x and develop the moment equation for that part. So it simply says if we cut our beam by the length of x, the moment created and the resultant force. The moment is the resultant force located at 1/3 of that distance, which is x from the base of the loading. And then let's develop the moment equation at x, and it just says summation of moment at x goes 0. It just says, let's see how it goes. So if we have the overall length of the beam, you can easily see the intensity of loading is W. So if we just go by a arbitrary length of X, we want to know what is the intensity of loading there. And that's a simple proportion of X over L times the overall intensity of W. So if we have this a intensity for this part, X over L times W, before reaching the total length, which is W, then we can easily see the resultant force is simply 1/3 of that part of half of the x over W times uh, half of x over L times W times the length, which is x. So summation of moment at x counterclockwise goes 0. It just says mx plus the resultant times the distance, which is a half of the x over L wx times 1/3 of xl, minus, because this is the clockwise, that's a half of wl, which is ra plus ma. These two are known, but just in case we show it like parametrically. And as soon as we have that, we can rewrite the moment equation as below. As soon as we have our moment equation, we can integrate it twice to get the delta function. So the first integration gives us the theta and equation, and integrate it once more, it gives us the delta function. So be careful with each integration, a constant is created. So when we have the moment equation parametrically, we can just jump down to the boundary conditions, which is at x equal to 0, theta is 0, it's our first boundary condition, and at x equal to 0, at the fixed support, there is no rotation, theta is 0, there is no up and down movement, there is no sway. Delta is 0 as well. So if we combine these two boundary conditions with our theta and delta equation, it simply says a and 1 gives us this first constant goes 0, so c1 is equal to 0, and b and second equation gives us the second constant c2 is equal to 0. As soon as we have our constant as well, we can simply rewrite our delta equation and replace it by the overall length of L at free end B, and thus our delta maximum is equal to a negative sign is due to downward movement, a downward movement of 11 over 120 WL to the fourth over EI. Thank you. We'll solve more problems in beams.